When selecting an overcurrent protective device for a transformer, adherence to the National Electrical Code, specifically Table 450.3, is crucial. This table dictates the maximum allowable overcurrent protection for transformers. The question involves a 300 kV three-phase transformer supplying a 208-volt lighting and appliance panel. The full load ampacity is calculated to be 833.33 amps. Table 450.3 permits the secondary overcurrent device to be set at a maximum of 125% of the transformer's rated current. This calculates to 1041 amps. The query is whether a 1200 amp breaker can be installed because it is the next standard size breaker listed in National Electrical Code 240.6. It is over 800 amps, and the conductors are rated as per 240.3. National Electrical Code Article 240.3 states that overcurrent protective devices shall have sufficient interrupting and closing ratings and shall be suitable for the conditions of operation. This essentially means the breaker must be capable of safely interrupting the maximum fault current that could flow through the circuit. National Electrical Code Article 450.3 states that the secondary overcurrent protection shall not exceed 125% of the transformer rated current. Therefore, the breaker must be set at a value that does not exceed 125% of the transformer's rated current, or 1041 amps. 1200 amp breaker exceeds the maximum allowable setting of 1041 amps. Because of this, the 1200 amp breaker would not be able to provide the required protection. It could potentially allow excessive current to flow through the circuit, risking damage or fire. Therefore, an adjustable breaker set at no higher than 1041 amps must be installed to meet the requirements of Table 450.3 of the National Electrical Code. The critical point lies in the explicit requirement of Table 450.3 that the overcurrent protection does not exceed 125% of the transformer's rated current. While National Electrical Code 240.6 provides standard breaker sizes and 240.3 C addresses conductor ampacity and breaker suitability, they do not override the specific limitation outlined in 450.3. B for transformer protection. Choosing a breaker involves firstly calculating the transformer's full load current. Secondly, determining the maximum allowable overcurrent protection according to Table 450.3, which is typically 125% for secondary protection. Thirdly, selecting an adjustable breaker that can be set at or below the calculated maximum. Even if a larger standard breaker size exists, it cannot be used if it exceeds the 125% threshold. The primary reason for this stringent requirement is to protect the transformer itself from overcurrent conditions. Transformers are susceptible to damage from prolonged overloads, which can lead to overheating and insulation breakdown. By limiting the overcurrent protection to 125%, the National Electrical Code aims to prevent such damage and ensure the transformer's longevity and safe operation. It's essential to remember that the overcurrent protection device, whether a breaker or fuses, is intended to protect the transformer, not just the downstream conductors. While conductor protection is also a critical aspect of electrical safety, the transformer's vulnerability to overcurrent damage takes precedence in this specific scenario. An important consideration is the breaker's adjustability. If using an adjustable breaker, verify that it can be accurately set and locked at the desired value, ensuring that it remains within the 125% limit. The breaker's trip curve should also be reviewed to ensure it provides adequate protection for both overload and fault conditions. In addition to the overcurrent protection, the transformer must also have appropriate short-circuit protection. This is typically provided by the same overcurrent device, but it's important to verify that the breaker's interrupting rating is sufficient for the available fault current at the transformer's secondary terminals. The available fault current depends on the utility's supply capacity and the transformer's impedance. A higher impedance transformer will limit the fault current, while a lower impedance transformer will allow a higher fault current. The breaker's interrupting rating must be greater than the calculated available fault current to ensure it can safely interrupt a short circuit. Furthermore, proper coordination between the transformer's overcurrent protection and any downstream overcurrent devices is essential. Coordination ensures that the downstream devices trip before the transformer's breaker trips, minimizing the extent of any power outages. Coordination studies are often performed to determine the appropriate settings for all overcurrent devices in the system. The physical installation of the transformer and its overcurrent protection must also comply with the National Electrical Code. This includes proper clearances, ventilation, and grounding. The transformer should be installed in a location that provides adequate ventilation to prevent overheating. The overcurrent protection device should be readily accessible for maintenance and inspection. The transformer and its enclosure must be properly grounded to provide a path for fault current to return to the source, minimizing the risk of electric shock. Regular inspections and maintenance of the transformer and its overcurrent protection are crucial for ensuring continued safe and reliable operation. Inspections should include visual checks for any signs of damage, overheating, or loose connections. The breaker should be tested periodically to verify its proper operation. Any necessary repairs or replacements should be performed promptly to prevent potential hazards. In summary, selecting the appropriate overcurrent protection for a transformer requires careful consideration of the National Electrical Code requirements, specifically Table 450.3. The overcurrent protection must not exceed 125% of the transformer's rated current, and the breaker must have sufficient interrupting rating and be properly coordinated with downstream devices. Proper installation, grounding, and maintenance are also essential for ensuring safe and reliable operation. Failure to comply with these requirements can result in transformer damage, fire hazards, and potential electric shock. Remember to always consult with a qualified electrical engineer or electrician when designing and installing transformer protection systems. They can provide expert guidance and ensure that the system meets all applicable codes and standards. Keep in mind that electrical codes and standards are subject to change, so it's important to stay up to date with the latest revisions. The National Electrical Code is updated every 3 years, and it's crucial to use the most current edition when designing and installing electrical systems. Local codes and regulations may also apply, so be sure to check with your local authorities for any additional requirements. By following these guidelines and seeking expert advice, you can ensure that your transformer is properly protected and operates safely and reliably. Understanding the nuances of transformer protection is paramount for electrical safety and the longevity of electrical equipment. The National Electrical Code provides a framework, but applying it correctly requires a thorough understanding of electrical principles and practical experience. A common mistake is to simply choose a breaker based on conductor ampacity without considering the transformer-specific requirement. While conductor protection is important, it should not override the transformer's overcurrent protection needs. Another mistake is to assume that a larger breaker is always better. In the case of transformer protection, a larger breaker can actually be detrimental, as it may not trip quickly enough to prevent damage to the transformer during an overload. Therefore, it's crucial to carefully calculate the maximum allowable overcurrent protection and select a breaker that is appropriately sized for the transformer. It is also important to differentiate between overload and short-circuit protection. Overload protection is designed to protect the transformer from prolonged overcurrent conditions, while short-circuit protection is designed to protect the transformer from sudden high-current faults. The overcurrent protection device should provide both types of protection. Some breakers have adjustable trip curves that allow you to fine-tune the protection for both overload and short-circuit conditions. These breakers can be particularly useful for transformer protection, as they allow you to optimize the protection for the specific application. However, it's important to understand how to properly adjust the trip curve to ensure that the transformer is adequately protected. In addition to the breaker, fuses can also be used for transformer protection. Fuses have a faster response time than breakers, which can be advantageous in some applications. However, fuses must be properly sized and coordinated with downstream devices to ensure selective coordination. Selective coordination means that the downstream fuses will trip before the upstream fuses, minimizing the extent of any power outages. Achieving selective coordination can be challenging, but it's an important consideration for critical applications. The choice between breakers and fuses depends on a variety of factors, including cost, performance, and maintenance requirements. Breakers are generally more expensive than fuses, but they can be reset after a trip, while fuses must be replaced. Breakers also offer more flexibility in terms of adjustability and coordination. However, fuses may provide faster protection in some cases. Ultimately, the best choice depends on the specific application and the priorities of the user. Regardless of whether you choose breakers or fuses, it's important to properly document the overcurrent protection system. This includes recording the breaker or fuse size, type, and settings. It also includes documenting the calculations used to determine the overcurrent protection requirements. This documentation can be valuable for troubleshooting, maintenance, and future modifications to the electrical system. It's also important to train personnel on the proper operation and maintenance of the overcurrent protection system. This includes training on how to reset breakers, replace fuses, and inspect the system for any signs of damage or overheating. Properly trained personnel can help to prevent electrical accidents and ensure the safe and reliable operation of the transformer. Finally, remember that electrical safety is always the top priority. When working on electrical systems, always follow safe work practices and use appropriate personal protective equipment. If you are not qualified to work on electrical systems, hire a licensed electrician to perform the work. Electrical work can be dangerous, and it's important to take all necessary precautions to prevent accidents.